Hey, welcome to question 3 of the problem solving session for chapter 9, where we're focusing on reactions of alkynes. So in question number 3, part A here, we're looking at phenylacetylene reacting with two HBRs. So phenylacetylene, that is a structure that we haven't talked too much about previously in terms of the nomenclature of this, but we can sort through this. So acetylene is a 2-carbon alkyne, also known as ethyne. So I'm going to plug that 2-carbon alkyne in. And then the term phenyl here refers to an aromatic ring that is a branch off of a molecule. So our phenyl ring is going to be this aromatic ring right here. That will be our structure of phenyl for that aromatic ring. Acetylene, because we have a 2-carbon group here, right here. And we're reacting that with 2 HBr. So in order to predict the product of reacting this phenylacetylene with HBr, I am going to start by walking through at least parts of the mechanism for this to show key steps so that we make sure that we are getting to the correct product here. So sketching out a bit of the mechanism here, phenylacetylene, we're going to take our pi bond, bring that over to pick up a proton from the acid. Anytime you're reacting an organic molecule with an acid such as HBr or H2SO4, always expect that the first step of the mechanism is going to be protonation of the organic molecule. Always expect that the organic molecule, in this case the phenylacetylene, is going to be grabbing a proton from the acid because that acid is so eager to lose a proton that any pi bond in our acid or lone pair of electrons in the acid is going to be able to come over and grab that proton. So let's go ahead and take a look at what's going to result from that. So we're going to get bromide anion. And we will have added that proton across the carbon-carbon double bond. Alkynes love to undergo addition reactions. So I'm sketching out the skeleton here of our alkyne that now has picked up a proton. We have to ask, where is that new proton that we've picked up from HBr going to go? Is it going to go on the carbon on the left or the carbon on the right? And here, just like we were doing back in chapter 7 with addition reactions, we're adding acid across the carbon-carbon double bond. We follow Markovnikov's rule, which I'm going to abbreviate here just as Mark's rule as a reminder to you to follow Markovnikov's rule when deciding where to place that new proton. So that new proton in red here on the left is going to go right here because Mark's rule says that you place the proton that is newly added onto the less alkyl substituted carbon, or in other words, the carbon that has more hydrogens directly bonded to it is where you're going to place that new proton. So it's going to go right here. And that is going to result in placement of a positive formal charge over here. So then with that in mind, now we have our carbocation intermediate, and the bromide anion acts as a nucleophile to come in and form a covalent bond to that carbon atom. So just sketching out the mechanism really briefly here, our lone pair electron comes in, forms a bond to that carbon, and that's going to lead us to our next organic product here where we have our phenyl group directly connected to our carbon atom, which has our bromine bonded there, and then the next carbon has the 2 hydrogens. But there's more, because in this reaction, we didn't indicate that we were reacting with just one equivalent of HBr, which is what we did here. Instead, we indicate that we're reacting with 2 equivalents of HBr. So don't stop here unless we're only reacting with one equivalent of HBr. If we have 2 equivalents, which is what we have here, then we need to keep going. And so the second equivalent of HBr is going to behave similarly to the first equivalent in that we are going to take that second equivalent of HBr, and acids love to act as acids. So in other words, what's going to happen is that The pi bond from the alkene going to come in, grab a proton from the acid. That forces the bond between H and Br to break. And with the bond between H and Br breaking, we get protonation of our molecule here. That pi bond no longer going to be there. Instead, it's a bond to the new proton, as we're showing here with our electron pushing arrow. And we decide again where to put that proton by following Markovnikov's rule, which indicates that new proton is going to go here on the carbon on your right. Originally a CH2, picked up that extra proton, now a CH3 following Mark's rule. And our carbocation now resides here at this position. And if you were wondering about stabilization of this intermediate, it would be possible to show a resonance structure here where the lone pair of electrons came down to form a pi bond between carbon and bromine. And that would be a second resonance structure there corresponding to a double bond right here and a positive charge on the bromine that would illustrate the sharing of that positive charge across two different atoms, and that would help stabilize this intermediate. I'm not going to show that here because our main goal is just to predict the major organic product, so I'm trying to get cut to the chase as efficiently as possible, but I wanted to make sure you're aware of that in case you're ever asked to give a mechanism and show how the intermediate is stabilized by resonance. So now at this point, we have our carbocation. Out of this step of protonation, we also generated bromide anion, which is a terrific nucleophile. This nucleophile is going to attack the carbocation like so and lead us to our final organic product here. So we've got our aromatic ring, and we're directly connected to a carbon atom that has two bromines bonded to it now, and then our CH3 group. And I'm not going to write out CH3 explicitly, but keep in mind that end of the line there represents our CH3 group. So our final major organic product of this reaction, boxed in here in gray, is going to be this geminal dihalide. We call it a geminal dihalide or a gem dihalide because geminal means that the two groups, the two halogens in this case, are bonded to the same carbon atom. Hence, geminal is the term that we use there to describe two groups that are bonded to the same carbon atom. So that's our major organic product there. Similarly, we're going to go on to the next part, part B here, where we are going to carry out an analogous reaction as we did in part A to get a little more practice at this. Hex 1-ine. So we need a 6-carbon chain. So we have our 6-carbon chain, and we're reacting with HCl. Pi bond comes over, forms a covalent bond to the proton. Bond between H and Cl breaks. So we have our chloride anion. And also we have our carbocation intermediates, where again we follow Mark's rule to decide which of these two carbons, the alkyne carbon on the left or the alkyne carbon on the right, are going to pick up the proton. And we want to plug that proton following Mark's rule onto the less alkyl substituted carbon, which is going to be this one on the end here, has fewer carbon-carbon bonds. So that's where the proton is going to land in this direction. So we're going to plug that proton onto this carbon on the left. So let's go ahead and do that. So that's going to give us H2C here at the left end terminal of the molecule, double bond on a carbon with a positive formal charge on it, and then a 1, 2, 3, 4 carbon chain to give us our carbocation intermediate here. Then at this point, analogous to up top, we have our nucleophilic halogen, in this case it's a chlorine down below, come in and form a covalent bond to the carbocation. So follow that same pattern we did up top, where nucleophiles love electrophilic carbons. Carbocations are great electrophiles because they're very electron deficient with that positive formal charge. So that forms our bond, and then we'll go ahead and draw out the product resulting from that, plugging in my 6-carbon chain. And now at this point then, we bring in another HCl because the reaction says that we're doing 2 equivalents of HCl here. So pi bond comes in, grabs that proton, forces the bond between the chlorine and our hydrogen to break, giving us chloride anion, and our next carbocation intermediate follow Markovnikov's rule again, which means that the carbocation is going to be here at position 2 of our 6-carbon chain. Then finally, we bring in our nucleophilic chloride. It attacks the carbocation, and that's going to give us our grand finale product here, which will be another Geminal Dihalide type product. So chlorine, chlorine, and I'll go ahead and put a box around this product. So you should at this point be comfortable with predicting the major organic products of these types of reactions where you're adding HBr or similar haloacids across the carbon-carbon triple bond is either one equivalent of HX acid being added or, as we're showing here, 2 equivalents being added. If it's 1 equivalent, you stop at this halfway point through the reaction where we've added 1 unit of HCl or HBr. If we go all the way, then we need to add that second one by doing the second part of this mechanism.